So we should be streaming now. Okay, right. So we're now on YouTube as well. So before I introduce the first keynote speaker, I wanted to briefly announce the winner of the Best Paper Award for this year's PEPM. So the winner is a talk we saw earlier today, a paper we saw earlier today, Counterexample Generation for Program Verification Based on Ownership Refinement Types by Hideto Ueno, John Toman, Naoki Kobayashi, and Takeshi Tsukada. So well done. I'm afraid we don't have any sort of actual prizes, but congratulations, and you can stick that on your CV. So now on to the main event. I'm very pleased to introduce Julia Lawall as our first keynote speaker, and this is the closing talk of today's workshop. Julia has been involved in the area of PEPM for a long time, I guess. So she's currently a research scientist at INRIA in Paris. Prior to that, she was in Copenhagen. And I guess she was working more directly on partial evaluation type research in the past, but her interests have moved towards doing all kinds of other things, in particular systems programming. But what's nice about this talk, I hope, is that she's bringing together both her past interests and what she's been working on currently. So thank you very much, Julia. Can you take it away?
Okay, so thank you very much for the invitation. So I'm going to be talking about program manipulation of C code from partial evaluation to semantic patches for the Linux kernel. So I'm going to start with partial evaluation. I'd just like to mention that I'm certainly not the originator of partial evaluation. I didn't even work on it in its early days. My contribution was in the second half of the 1990s, where I worked on the partial evaluator Schism for Scheme and the partial evaluator Tempo for C, and then it was later extended to Java. So, but I'm going to start my talk at the very, very beginning, the origins of partial evaluation, the beginning idea that the proof of a possibility of existence of partial evaluation is Kleene SNM theorem, MN theorem, which dates from 1943. So in this presentation, I've specialized it to M and N being one, just to be concise. So the idea is for every Turing machine, TMSD, which Turing machine you can just think of as a program, having two arguments. And for all possible values of the first argument, S, there exists a Turing machine TMD of arity 1 such that if you run the first Turing machine and apply it to both arguments, then if you take the second machine and apply it to only the second argument, it will give the same result. So basically, what this part of the theorem is saying is that if you take a Turing machine that is a program of a certain form, then with the two arguments, then you can translate it into another Turing machine that is to another program that now has only one argument, but kind of behaves the same way as the original one. And then the second part of the theorem says, furthermore, there's a Turing machine S that allows TMD, the generated one, to be calculated from the original one. And so what this means is that there's an automatic approach. There's like some kind of procedure that can get us from one place to the other. And so this procedure is going to turn out to be what we today call partial evaluation. So basically the idea is partial evaluation because we have one of the arguments, which is S. We partially evaluate our program and we get a new one, which is somehow specialized to that value of S. So that's a bit abstract. So if we can think about it in terms of code, so I've written just in a random language, I chose ML. So we have a little function here. It has two arguments, again, s and d. It has a test. If d is equal to 0, then we return s plus 1. Otherwise, we return s plus d. So suppose we have our program and we know that s is going to be 4. So then basically we have a specialized function. Now that we know s is 4, we have a specialized function which is called fn prime. And this specialized function is going to, one way we could write out this specialized function is to just call the original function with 4 and d. So this is basically a proof of the Kleene-SMN theorem. It's easy to see that if we have any function, it has any number of arguments. If we know some of the arguments, then we can define a new function in a systematic way that is going to call the original function with the arguments we know and the arguments that we don't know. But this would be kind of disappointing. We know that s is 4, so maybe we could do a little bit more with that. A very simple thing to do, we could always systematically unfold the call to our original function, and then we'll get a new function that has a let s equals 4, and then just the original code of the original function. So again, this is another way we can show that that we can somehow prove the SMN theorem, because we have a systematic way of getting from the former one to the latter one. Of course, ideally, we would do a little bit more work. We can take that value of s and we can actually inline it to all of the places that we end up with. So if we do our let unfolding, then we end up with some code. We have our if, we have our then, and we have 4 plus 1, and we have 4 plus d. And if you were going to take the trouble to do that, then you might feel a bit disappointed to not somehow go all the way. So what we would like is the 4 plus 1 to turn into 5. And so now we get a specialized function. And this is the idea of partial evaluation, which is that when we have specialized our function with respect to some of its inputs, it's possible that there are some computations inside the function that can be evaluated. So that's the evaluation part, and then it's partial evaluation because we have only partial knowledge about the input. So what kind of evaluation can we do based on a partial knowledge of the inputs? So now we move forward to 1971. And Futamura was thinking about interpreters and compilers. So an interpreter is a program that has two inputs. It has a program as an input and the input of that program as an input, and it analyzes the program on its input, and it produces in some manner a result. A compiler, on the other hand, it just takes the compiler takes only the program part as an input, and it translates it basically into some other language. So we started out with program prog, and we're going to produce prog prime. And this program in the other language, which is, if you think about something, a language like C might be assembly language or object code of some form, then it's going to have to be interpreted. This new program will have to be interpreted again to get this result. So these are concepts that are familiar when we think about programming languages. It's been a long time, certainly before 1971, that we had interpreters and that we had the idea of compilers. But Futamura was concerned about how can we actually write these things, especially how can we write a compiler? So writing interpreter seems pretty easy. You have all the information. You have the program, you have the input, and you just think about what should the program do on this particular input. If the program is some function, it takes x as an argument, and the result is x plus 1, then you're going to take your function, you take your input, you have x, you look up the value of x, you add 1 to it, and that's the result. On the other hand, writing a compiler, if one thinks about it, is actually quite a hard thing to do, because you have to figure out what things should you do and what things are you going to need to wait to have for the input. So you have to think about it, the computation in terms of these two different times of availability of information. So ideally, what we would like to do at a compiler is the compiler should take in the program and do as much as it can. But what is as much as it can? What operations does the compiler perform, and which ones should be left for the generated code? And if you think about it, if you think back to the little bit of code that I showed at the beginning, this is exactly what an issue with respect to the SMN theorem. The SMN theorem promises the existence of a tool that can be applied to an interpreter and the program to figure out what should be done. We have the interpreter, it takes two arguments, the program and the input, and this tool S is going to figure out the kinds of optimizations, the kinds of unfoldings that I showed in the little trivial example in order to generate new code, which will then be able to take the complete input as a result. So Futamura came up with the idea of the Futamura projections, which showed how to derive a compiler from an interpreter systematically using what he called partial evaluation. So in the 1980s, attention turned to how can we do this in a real way? So Futamura raised this challenge of actually implementing this S function for real programming languages. And this challenge was taken up by researchers in a number of countries, more or less at the same time, in Denmark, in France, in Russia, and so on. There were initial advances in tools for idealized languages, and then there was an interest in working on real programming languages, which is an issue that Futamura brought up in the beginning. So at the time, it was decided to think about functional languages because that kind of put aside some issues such as side effects, aliases, pointers, and all these kind of complicated things. And in particular to focus on Scheme because Scheme has a very nice notation, which is very easy for program analysis and program manipulation. It's very easy to parse and it's very easy to generate executable code. And so by actually taking this idea and applying and implementing it for a real language, there were it led to a number of conceptual advances. Binding time analysis, which is a way of kind of separating the partial evaluation process into understanding what we know and what we can do, and actually performing the optimizations based on what we know and what we can do. There were other forms of specialization that were invented, such as data specialization, where instead of simplifying the code, you store specialized values in some auxiliary data structure. There's the idea of multi-stage languages, where you don't have just two. We just showed two arguments, S and D. So one argument comes in, is available at one time, and the other arguments are available at some later time. This can be straightforwardly generalized to having values that become available at different times. And finally, a number of people looked at actually realizing what Futamura had in mind, that is generating a compiler from an interpreter. And these various conceptual techniques made it possible to do that kind of thing for a real programming language. On the other hand, even though the techniques started to be quite well developed at the Scheme level, partial evaluation maybe didn't achieve the impact on the real world as one might have hoped. And so there was interest in, in part because Scheme was actually mostly used in academia. And so there was interest in thinking about other kinds of languages, in particular, moving to C. C is an imperative language. It introduces a number of new features, such as pointers, arrays, bits, and so on, to see what kind of impact they would have on partial evaluation concepts. And at the same time, there were also some experiments that had been done, particularly on operating systems code, where people had specialized certain system calls by hand, for example, and gotten great improvements. So it seemed like an area in which there was an opportunity for the kinds of optimizations that partial evaluation could do. At the time, there was also a growing interest in general in reliability of operating systems code. And so by being able to do transformations and optimizations automatically, that seems like a way to improve the reliability as opposed to doing things by hand. So several tools were developed. CMix was developed at Deku, and Tempo which I worked on in part, was developed in RAN. So this led to a number of conceptual achievements. Perhaps the most notable one is the work on alias analysis that was necessary for analyzing C code. So this led to Anderson's algorithm, which is one of the two main basic strategies for doing alias analysis in C that still remains used today. Another interesting conceptual improvement is runtime specialization. So when we're thinking about C, C is compiled directly to assembly code instead of somehow the assembly code is more accessible than in the case of functional languages. And so this brought about the idea of creating specialized programs out of fragments of binary code as opposed to out of fragments of source code. And it made it possible to imagine a code that's executing, and then somehow dynamically we realize that some arguments are always going to have the same values, and then generating on the fly a specialized version based on that information. There were also a number of new applications. Ray tracing, so that was originally done at a functional level by Torben, and then it was later redone in C. There was a great success in RAN about doing remote procedure calls. So the idea is that in a remote procedure call, you have some data structures which have some format. You need to package them up and ship them off. And so you can specialize all the code for doing that packaging process based on the types of the arguments. And also I worked on specializing the checkpointing processes at the Java level. Again, there's this idea which, since we know the type of data we're going to manipulate, we can prepare whatever tool we're doing in advance based on that type information. So the nice aspect of partial evaluation, I think, is that the user interacts with the interfaces. That is, we have the list of arguments. The user may know which arguments are often known and often have fixed values. The user can, for example, if you think of a library, the user may know that they are always often going to use the library with certain options. And so then it's desirable to do the specialization. The user doesn't have to actually know anything about the implementation of the library. Basically, the user provides their information, and then the partial evaluator is going to take care of all of the rest. The partial evaluator takes in the information and then figures out how to optimize the program, however it's implemented, according to what is provided. So as we saw before, we have an interpreter, and the user provides the code. The user doesn't have to know how the interpreter is written. The partial evaluator will just push the code around in the interpreter and optimize everything it can along the way. On the other hand, there's a great weakness here with this high degree of automation, which is that the tool is the tool that's going to decide how the values get propagated around. So I was thinking about it, it's like these kinds of toys where you drop some marbles in it, and then you want to try to get the marble to come out the other side. So the toy is organized in a complicated way. So it actually turns out to be a bit hard to get the marble to get all the way through. And so partial evaluation turns out to be sort of like that. We would drop our marble in the top. That's easy to do. We provide our static values, but those static values might get kind of stuck along the way. In general, overall, the choices that are made by the tool depend on whatever analyses the partial evaluator is going to do. And in some sense, the number of these analyses has accumulated. So in the functional language, we just had binding time analysis. Once you have C code, you have to worry about alias analysis and other kinds of side effect analyses that each analysis has intrinsic limitations, and the user doesn't really know the analyses in some sense limit the results that can be produced. And on the other hand, the user doesn't really know what the limitations of the analysis are. So all of this makes it very hard for the user to actually get out the answer that they expect. So this led to a lot of work on the idea of binding time improvements. So binding time improvements are transformations that can be performed to the code itself before the partial evaluation process in order to bring the known values together. So for example, if we have some code like what we have on the left here, so this is now written in an imperative language. We have some if, we have an assignment of x to s, we have an assignment of x to d. The partial evaluator has no idea which one of these is going to happen because the D is the unknown input, and so we don't know which branch is going to be taken. And so we can't actually do any simplification of this x plus 1. On the other hand, if we do a binding time improvement there, so if we reorganize the code a little bit, if we push the x plus 1 back into each of these branches, then we end up with the code return s plus 1 and return d plus 1. And now if we know the value of s, actually we can do some simplification. It's not very much in this case, but you can see how the structure of the code is going to determine what can be simplified during the partial evaluation process. So then there's a question, are we going to do this by hand? How is all of this is going to happen? If we have to do this by hand, then the user has to think a lot more about what the partial evaluator is actually doing. So we kind of lose all of our automation aspect. And there's another disadvantage is that we can't have so many different implementations of the code. If we reorganize the code so that it works very well with partial evaluation for one of the inputs, that might be detrimental to another one of the inputs. So it's kind of hard for the user to actually get the effect that they want. And another approach would be somehow to automate some of these common patterns that gives improvements. But again, then we get back to the same situation, which is that if the tool is making all of the decisions, then the tool has its advantages and its limitations, and these are very hard for the user to understand, and we end up with an unpredictable user experience. And further work in partial evaluation kind of went in this direction, identifying opportunities for specialization, kinds of code, design patterns of code that would specialize well, or allowing users to declare and check opportunities for specialization, like to say, you can specialize this function with respect to the first argument, but it's not going to be useful to specialize it with respect to the second argument. So basically, a conclusion is that automation is alluring. So the idea of partial evaluation is to be very automatic. You just give a little bit of information and then the tool figures out what it should do. But maybe predictability is actually the key to usability. So if we want to have something that people will find useful, we would like the user to be able to understand what's going to happen without having to know too much about the internals of the tool. And somehow all of the automation that is provided by partial evaluation is somehow contradictory to that, because it's hard for the user to understand what automation is going to happen and what they can expect. Okay, so now I'll turn to the second part of the talk. Basically, at that point in around 2000, that was the end of my own work on partial evaluation. The field has certainly continued in many different directions, and some of them thinking of more complex partial evaluators and solving these issues in different ways. A few years later, my interest turned to automating transformations of systems code, of Linux kernel code in particular. I contributed to the design, the development, and maintenance of Coccinelle, and this was in particular joint work with Julia Lawall, who also participated in the work on Tempo. And so we both had some kind of intuitions about what we felt like had worked well and not so well in partial evaluation. And sort of what I'm going to talk about in the second half is in part what is Coccinelle and how does it work, but also a bit about how our feelings about the successes and failures of a partial evaluation contributed to the design of Coccinelle. So in the case of Coccinelle, what we were interested in is the maintenance of large-scale software. So Again, note that I'm not saying that Coccinelle is supposed to be a replacement for partial evaluation. We're targeting a different problem. We have different design choices. But I just want to say consider how the influence of the experience with partial evaluation affected the design of Coccinelle. So a specific problem that we considered is that for some kinds of software development problems, developers know what kind of code they want to change and developers know what kind of changes they want to make. So we're targeting an audience that's a bit different than the partial evaluation audience. We're targeting people who are actually working on the implementation of the code. They know well what the code does and they know well what they want to change. What they want to do is they want to get some kind of large scale changes that can happen for them automatically. So our idea was that developers could benefit from a tool that would automate these kinds of changes. So our application area is the Linux kernel. Linux kernel is probably familiar to everyone. It's open source. It's used in all kinds of settings from smartphones to supercomputers. It has the feature of being very, very large. Today it's around 19 million, over 19 million lines of code, and it's continuously growing. And it changes a lot. Internally, it changes all the time. The functions, you get new functions. You have functions that are removed, functions that take extra arguments, things that have to be done in different ways to improve performance and correctness. So what we want is our concerns are how can we perform evolutions in such a large code base. So the idea is even in smaller code bases, even in like personal projects, you think, oh, this function is not really satisfying my requirements. It's not very easy to use. I forget what the arguments are supposed to be or something like that. But if I change it, then I'm going to have to go change the uses of the function in 100 other places, and that would be tiresome. So it's kind of a trade-off. So that's the problem that we want to solve. We want to make those kinds of changes happen automatically. And a related problem is in a very large code base, if somebody has made a problem once, probably someone else has made that problem, the same problem somewhere else. And so once a bug is found, how can we check whether it occurs in other places? So basically what these problems have to do with is they're concerned with the idea of changing code. And so our starting point in this work, we had the idea that it would be good to kind of meet the Linux kernel developers at the place with what their expertise is. Our starting point is the changes, is the way that Linux kernel developers reason about changes already. So the way that they reason about changes is the idea of a patch. So people who use Git and so on are probably familiar with patches already. It's basically a diff. It shows basically a fragment of code that needs to change. And some of the lines are annotated with minus to indicate that they should be removed. And other lines are annotated with plus to indicate that they should be added. So this is a simple and very common change in the Linux kernel. Basically, we have kmalloc, which is the kernel level function, memory allocation function, and we have memset, which fills all of the allocated memory with 0. And what we would like to do is just to simplify the code a little bit by replacing the combination of kmalloc and memset by a new function, kzalloc, which actually allocates the memory and does the zeroing at the same time. This is a pretty simple change to do, but it's actually not that trivial to find the opportunities for it because the kmalloc and the memset have to be in a certain relationship to each other, and they are not actually right next to each other. So it's hard to find cases in the code where actually both of them are present. So our simple idea was to take these kinds of patches, which Linux kernel developers are familiar with, and raise the level of abstraction from patches to semantic patches. So we're going to take a patch like this, which describes very precisely the kind of transformation that we want to perform. But it has the disadvantage that it only works in a particular place in the code. So we want to make it a bit more abstract so that it can be used in a more general way. And so to do that, we take this notation and then we turn it into this notation. So this is very similar, except that we have basically thought about some of these subterms are very important, and so we've kept them. We've kept the idea of kmalloc and of memset, and some of them are not very important. So actually, we want to make this transformation at every place where we have kmalloc followed by memset, but we don't really care what the arguments are, and we don't really care in what place the return value is stored. On the other hand, we do care about some relationships between things. So the return value of kmalloc should be the first argument of memset, and the first argument of kmalloc should be the last argument of memset. So all of this is expressed by what we call metavariables, which are declared here. So metavariables can be expressions or statements or identifiers, different any kind of term. You can also specify what their type should be and so on. So basically, we have a pattern which is describing what kind of term should be modified. The pattern is in a notation that's familiar to Linux developers because we have things that look like code, we have lines that are removed, and we have lines that are added. On the other hand, there's a little bit of semantics here. This ... operator is actually not just, I mean, basically the idea of the ... is just like a sequence of code between the kmalloc and the memset. But furthermore, in the case of semantic patches, the sequence is a sequence in the control flow path of the function. So in that sense, it's following the semantics of the code. So yes, it's we have this. We can abstract over the subterms via metavariables and the control flow path via ... So simple SMPL is the domain-specific language that Coccinelle provides for describing how transformation should be done. And then the Coccinelle tool applies the transformation across the entire code base. The main point was to start with what developers know and kind of build on that in a very minimal, the smallest way possible somehow in order to achieve the kind of automation that we want. And this project basically, the project began in 2004. The development of the tool began in 2006. And it was first released in 2008. So we can think about this tool that we're proposing in terms of the ideas of automation and predictability. So as compared to partial evaluation, we've gone down, I would say we've gone down a bit in automation, because in case of partial evaluation, you were just provided a few argument values. Here we have to actually be familiar with what the code is, and we have to actually script what is going to be the transformation process. The transformation itself is indeed fully automatic, but the developer has to tell the program, has to tell the tool exactly what should happen. On the other hand, we go up in, I would argue that we go up in predictability. The transformation follows the script in the way the script is written. So the user has to specify, for example, that kmalloc comes before comes before memset. And if the code actually follows that pattern, then the transformation will happen as it's described. So this makes it predictable. The tool is not doing any kinds of other analyses that the user has to understand. So we can see what kind of success this basic approach has had. This is a graph of the use of Coccinelle over time. Is not surprisingly, in the first few years, it was mostly the Coccinelle developers who were using Coccinelle. But you can see in the later, more recent times, the use by kernel maintainers has been steadily increasing, as well as the other use by other kernel developers. Today, there are over 8,500 commits in Linux kernel that mention Coccinelle. We did a study in 2017, a bit detailed about how people have used it and who has used it and so on. And at that time, we found that among the kernel developers who have done one commit that touches 100 files, so that's like really a huge at the Linux kernel level, about almost half of these people have at least one commit that uses Coccinelle. So somehow we feel that we are getting to the kinds of people who need to do these very large-scale changes. There are also around 60 semantic patches which are available in the Linux kernel source tree. And there's a Linux kernel make target that actually runs them. So on the one hand, people can use Coccinelle without having to learn the language, but on the other hand, they can also use these semantic patches as a reference to try to express the things that they want to do by themselves. So now I'm going to talk a bit more, kind of go into a bit more detail about how did we get here. So on the one hand, I would say I want to argue in this talk that the part of the success of Coccinelle is this idea of balancing automation and predictability, ensuring that the user is going to get out basically the result that he expects. But there's some other design decisions, I think, that also have contributed to its success. So I'm going to think about 4 design dimensions, which are expressivity, performance, correctness guarantees, and dissemination. And so we can see what decisions we started out with and how they withstood the test of time. So in terms of expressivity, our original hypothesis was that Linux kernel developers will find it easy and convenient to describe needed code changes in terms of fragments of removed and added code. So basically, our idea was at the moment, Linux kernel developers are describing changes in terms of patches. So probably everything they are going to need to do is basically like a patch. So like the specification that I showed previously. So that was the basic idea. That was like kind of the scope of the tool that we wanted to provide. When it was confronted with the real world, of course, there was necessity to have some adaptations. We certainly had to add some new kinds of features, new kinds of meta variable types, and so on. The C language is very big. Another thing that was already considered from the beginning was this ... operator. The ... operator allows you to do match everything between one point in the code and another point in the code. But often in practice, it's useful to specify that some things along the way should perhaps not contain certain things. For example, if we have assigned a variable, matched the assignment of a variable in one part of the rule, then we can go on and we might want to say that the variable should not be reassigned along the way. Remember that Coccinelle itself is not doing any kind of analysis whatsoever. If some kind of analysis like that is needed, then the person has to specify it in the rule, and then they can actually see what's going on. There's some other features that we found useful over time. 2 of them are the position variables and scripting language rules. So position variables are like meta variables, but they don't match terms like we had the expression x and E1 and E2 previously. They are meta variables that match the position of something. So once you have the position of something, then you can start making patterns that say the position of this thing should be different than the position of this other thing, or the position of this thing should be the same as the position of this other thing. And so that gives a much more fine-grained control over the matching process. And then the second feature is scripting language rules. So the basic idea of Coccinelle is that you should express everything in terms of pattern matching against code, but sometimes in practice, one would like to do other kinds of computations. The original goal for scripting language interface was to find more complicated forms of bugs. For example, buffer overflows, where you want to try to do some kind of reasoning about what are the possible values of different variables and whether they are outside of the size of the buffer. That didn't work out terribly well in practice. It was kind of complicated. The rules became somehow more complicated than was really useful. But the scripting language is very useful for reporting errors, counting, doing statistics, and so on. So just as a quick example, this is a rule that was written by some Linux kernel developers. And here we are, what they wanted to do is to be sure that certain functions are never used anymore in, in any new code in the Linux kernel. This is another small extension to the syntax of coccinelle of simple, which is a disjunction. So we can either match this pattern or we can match this pattern. But basically the idea is that they match calls, arbitrary calls to either of these two functions, which are somehow deprecated. We record the position of those function calls, and then here we use some scripting code that is going to print out an error message that indicates those positions. If we have new features, it's interesting to see if other people actually use them. The only information we have about what other people do is when they put commits in the Linux kernel that actually contain semantic patches. And there are a number of commits in the Linux kernel that have that property. We found when we looked in 2017, about 20% of them use position variables, about 5% of them use scripts. About half of these come from outside of the coccinelle team. So we know that people outside are able to understand these features. And actually all of the semantic patches in the Linux kernel use both of these features. And so then people have some examples of how to use them. The next issue we consider is performance. So basically our goal is that the tool should be usable on a typical developer laptop. As I mentioned initially, the code base is really big. When we started the project, it was around 5 million lines of code. Now it's around 19 million lines of code. So that's, I mean, it was big to start with, and that's a big change. Even at the 5 million lines of code, we knew it was a lot. And so we made a number of decisions that the rules actually apply only intra-procedurally. So you write a rule and it works on basically one function at a time. A semantic patch can have a collection of rules, and that collection of rules is applied one file at a time. We only work on the C files. We try to avoid including header files. We don't expand macros. That has a good benefit for performance because then we don't have to find the definition of those macros. But it's also very good for what our goal is, which is source-to-source transformation. If we were to expand the macros, then we would have trouble producing source code in the end that looks like the original code. And as I've been kind of emphasizing, we do some type inference so that people can make metavariables that depend on the type of the expression that should be matched, but there's no other program analysis. So this mostly worked pretty well for performance, but the code is still very big. We have some heuristics for the parsing process that may require iterating over the code multiple times. And so we had to do some further optimizations. One of them is indexing, so finding out which files contain which words, and then we can look at our semantic patch. For example, the one we had before, if there's no kmalloc and there's no memset, there's no point in looking at that particular file. So that gives a big improvement. And then we also offer parallelism. Coccinelle works on a file at a time, so it's very easy to parallelize. And so the performance is pretty good. In many cases here you see this is on a standard laptop. We see in many cases it just takes a few seconds, and indeed in many cases the various optimizations mean we only consider a few files. When we consider all of the files, so this is like over 40,000 files, maybe the running time gets up to maybe a couple of minutes. And there's some pathological cases where we have to search through very complicated control flow paths where it actually might take a longer amount of time. But in general, a typical Linux developer will only be working on a small part of the code at once. And so they may only want to run the rules on that small part of the code that they're working on. The third issue is correctness guarantees. So basically, the idea of the philosophy of coccinelle is we're not going to check correctness. We ensure that the syntax of the language is preserved so that if you replace if you remove a statement, you need to add another statement or just leave it alone. You can't replace, for example, a statement by an expression. But that's all. And so there's a number of advantages in this. Bug fixes and some kinds of evolutions might not be semantics preserving. It might just be the goal of the transformation you want to do. And also it increases greatly the efficiency, because many kinds, in a complicated system like operating system kernel, many kinds of correctness properties might be very hard to actually infer. The developer has a good knowledge of the code, and we basically just want to allow the developer to express his desires to change the code. The developer knows the code base, he knows the invariants and so on. And so we want to just let him express the kinds of changes which are relative to his knowledge. So we feel that mostly just giving the developer control over readable rules is somehow good enough. So if the developer can write a rule, he can test the rule, it might not work, and then he can kind of try it again. But since the rules are very close to the code and they're easily understandable, they're also easy to improve. There've surely been some bugs that have been introduced by the use of coccinelle, but I think one could argue that in most of those cases, it's because the person who was writing the rule didn't have a complete understanding, and not because the tool was somehow doing the wrong thing. Finally, to get people to use a tool, you have to make them aware of it. So our main strategy in this direction was to show by example. So we fixed a number of errors in Linux kernel. We made a number of evolutions, such as the kmalloc and memset one that I showed previously. People were interested in the way that it could do many, just kind of get rid of some problems completely all at once. There was some problems with the patch review policy of Linux, because every patch has to be reviewed by the maintainers of the affected code, and coccinelle somehow makes it too easy to make large-scale changes, and then the reviewing can be more challenging afterwards. Since then, we've developed some tools for breaking down patches into separate commits so that they can be sent to the individual maintainers. Basically, first we started using it so people could get an idea of it. Then it was released in open source. We organized some workshops. We presented at some conferences. Some other Linux developers wrote some articles about it. So that helped a lot in showing to people that it was a genuinely usable tool. So basically, we have considered these four design dimensions, and we have seen mostly that our original decisions held up. One thing that we have done over the last 15 years is to avoid creeping featureism. We do one thing. So we allow you to express the changes that you want about your code in terms of patterns. There's certainly some kinds of changes where kind of the greater automation provided by a system such as partial evaluation could be useful. But we wanted to stay within the boundaries of something that we know that works well. We meet the users at their level of expertise, and we have emphasized predictability over full automation. So just a little bit more detail about the impact. In terms of change lines, these numbers come from 2017. We have mostly had impact on device drivers, but coccinelle is relevant to code that appears all across the Linux kernel. We've also looked at what maintainers have done with coccinelle. So maintainers are people who are responsible for specific parts of the Linux kernel code and are generally more experienced developers. And so we can see that they have used it mostly for cleanups and somewhat for doing bug fixes. Indeed, the Linux kernel is quite open to the use of tools, and there have been a number of tools that have been developed for finding bugs in Linux kernel, whereas coccinelle is the only one that allows doing these, actually doing the program transformation part. And finally, a few concrete examples. For example, the TTY code removing unused function argument. Since it was unused, this is a fairly simple transformation, but it affected 11 files. One has to go around and visit all those files, be sure to find the right function, update it, and so on. Similarly, eliminating a redundant field in a data structure. This time 54 files were affected. And then an even bigger change, interrupts. interrupt handlers. Interrupts is a concept that is completely pervasive to an operating system. And so removing an argument from an interrupt handler affects a very large number of files, almost 200 files. And this is a somewhat challenging transformation because in some cases that argument is actually useful to the function. And so the function also has to be changed, not just to remove the parameter as was done in the TTY case, but also to figure out how to reconstruct the argument in the few cases of the functions where it's relevant. There's also the issue that interrupt handlers, as I mentioned, it's across the entire Linux kernel. It's in code which is specific to different architectures. And so the kind of trivial strategy of simply making some changes and then seeing what breaks when you compile doesn't work because you have to choose exactly the right configuration options to be sure that different lines of code in the Linux kernel will actually be compiled. So in conclusion, one thing that we have learned from the success and the adoption of Coccinelle is that maybe the predictability that it provides can be worth losing some of the automation. So we don't offer a completely general, completely automatic transformation system. What we offer is the ability for the programmer to kind of program the transformation by himself. So the programmer doesn't have to think about the internal representation of a programming language. So that's kind of what the tool buys for the programmer. But the programmer does have to think about exactly what changes should happen, what kinds of lines of code are affected, and so on. So as I mentioned, there have been over 8,500 commits in Linux kernel that use Coccinelle. There's many external users that is outside of our research group. There are also users who are not applying it to the Linux kernel, but I don't have that much information about exactly what they're doing. Coccinelle is available on most Linux distributions. And it has also, from a research point of view, it has led to a number of different research projects. I think just the direct interaction with Linux kernel community has given a better understanding of what their problems are and what their problems are in using Coccinelle. So we have developed a prequel, which is a tool for doing commit history searches. So it's basically using the idea of changes as can be described by Coccinelle not to perform changes, but to search for patterns that match those changes in the history. Spinfer is a tool for inferring semantic patches. So then we're going to kind of trying to get back some of the automation. But it's still the case that in the result of Spinfer, the person can look at the rule that is being offered and can understand what's going to happen and have some ability to predict what the result will be. And finally, PatchNet is going in a different direction, where we use machine learning to identify bug fixing patches. So overall, I think Coccinelle has had quite a pervasive impact on Linux kernel, such that probably everybody using this talk uses some Coccinelle modified code. Even if you're not using Linux, you're using Linux indirectly on web pages, mail servers, and so on. And all of this is publicly available at the shown website. So thank you.
Thank you very much, Julia. It was a very interesting talk. Let's thank Julia. Great. I think I'm going to abuse my position as chair to ask the first question, and then I'll invite further questions. So I was very pleased that you're stressing the importance of predictability. I think it's often underappreciated, particularly when people have you have your fancy new tool, it's able to do really powerful things. But if it's not predictable, then it's kind of useless in practice. But I wonder, do you have a good idea of what predictability really is in terms of a sort of mathematical definition of what you mean by predictability? I imagine there might be various different interpretations one could come up with, maybe relating to different notions of continuity or something. I mean, is this something you've thought about at all?
No.
No.
I think it's an interesting question. And I mean, I think I also maybe exaggerated a little bit, because Coccinelle is not 100% predictable. If it can't parse your code, it won't be able to do what you expect. And so users sometimes write to us and complain, like, why didn't it, it transformed 100 other places. Why didn't it transform this one? So it's not 100% predictable either. I don't know, it seems like a hard thing to formalize, because it relies in some sense on all the things that we were trying to get away from. So it relies on the semantics of the specification language. And in the case of Coccinelle, maybe we would like to give people the illusion that they understand the semantics. But it's actually an illusion. The semantics is actually fairly complicated and involves temporal logic and the analysis of the control flow paths and so on. And so it could be hard to kind of reconcile what the semantics, the actual semantics of the code is, and what is the model that is in the user's head.
Mm-hmm. Maybe you can come up with a more, I don't know, syntactic notion. I don't know, but anyway, no.
I mean, there's sort of a continuum. There's like real patches; they're completely predictable. There's like, if you find this sequence of characters, then you're going to get this transformation. So I don't know.
Okay, well, thanks for that. Now,
Yeah, I've asked for a comment, and it's about this predictability. So there's a similar problem with parallelizing compilers, that they might take some Fortran programs and generate good parallel code, but if you just make tiny modifications to your code, then it's no longer parallel at all. So there's increasing interest in making all the parallelism explicit in the code, rather than relying on automatic tools to vectorize your code. And in that context, it seems that predictability is something that small changes should not really have big impacts on the results you get. And I know from experience that in partial evaluation, that is definitely the case, that small changes to a program can make really big changes to the results you get by partial evaluation.
Yeah, I think that's a very good point. It's a very good analogy. And there's another analogy, which is a comment that I've heard about the Haskell type system, which is that as more and more features got put into the Haskell type system, you could type check more and more complicated programs, but it got more and more the case that if a person made a very small change to their program, then it wouldn't type check anymore. And it was very hard for users who weren't expert in the particular type features that were being offered by Haskell to understand in advance whether their program was going to be able to type check. So this idea of a little delta is perhaps a key to trying to understand the idea of predictability better. The idea of, if you make a small change, is it still going to, is a small change in input going to turn out to be a small change in the output?
Mm-hmm. That was what I meant by continuity.
Yeah, okay.
But yeah, I realize it may not be easy to formalize. Do we have some more questions? And you can ask questions on here, on Zoom, or on Clouder if it doesn't crash, or on YouTube.
Well, I have another question. You mentioned that your parsing uses backtracking, and that can sometimes cause very long execution time. So have you considered, instead of using backtracking, to use something like generalized LR parsing, which tries to do basically the same thing as backtracking, but in a way so it merges paths as possible? Any thoughts about that?
So I think I use the word backtracking in a bit too loose way. Basically, what the parser does is it tries to parse things, and then it tries again, and then it tries again, and then it tries again. It tries 4 times. And each time it might expand more macros, something like that.
Okay, I see. So it's not a generally backtracking parser.
Yeah,
Thank
no.
you.
No.
Okay, well, we're at the end of time. So if there are no more questions, then well, you can continue the discussion on Clouder.
Yeah.
I
believe there's one more question. Akira.
Akira, do you have a question?
Like
I was wondering whether Akira was responding to a different message.
Okay, yeah. So, okay, no problem then.
Okay.
Yeah, so great. Thanks to everyone for coming along today.
Okay, thank you.
And thank you very much for your talk again, Julia. Let's clap again, maybe me and Torben and anyone else who wants to unmute.
Okay.
And yeah, we'll be resuming again tomorrow at, well, actually at 3 o'clock Central European time. Because today's talks were sort of geared towards our people in Eastern time zones, and tomorrow's accommodate people who are in the US.
Yeah, and both of them